if we have a roller coaster car going around a vertical circle like this, we can approximate that by drawing it as just a circle. Now, this roller coaster cart can be anywhere in that circle, from position 1 down here at the bottom to position 2 along the side, or position 3 up here at the top, or anywhere in between. We can analyze the motion of this and the forces experienced by this car anywhere. Now, we won't analyze this one. The reason is because the values that we obtain end up being somewhere in between the two extreme values, the top and the bottom. We will select only the top and the bottom to analyze because they provide for us the extremes. Now, when we have an object at the top of a vertical circle like that, whether it's a roller coaster car at the top of a roller coaster track, or whether it's, like I did in the demonstration yesterday, a bucket of water at the top of a vertical circle, it doesn't really matter. And then we have another one at the bottom. The strategy that we follow is the same as the strategy that we follow any other time we have multiple forces acting on an object. We draw a Freebody diagram. Now, the Freebody diagram for these two pictures that we see up here going to look similar, but not the same. What are the two forces, the same two forces, that act on both of them? What's one of them? Yep, gravity. Gravity acts down on both of them. If these two carts are the same carts, then the force of gravity acting on the first one would be the same value and direction as the force of gravity acting on the second one. What's the other force that we have acting here? Ben? The normal force, good. The normal force acts which way when you're at the top of the circle? Towards the center of the circle. Acts in the same direction as gravity. Now, we're drawing it the same length as gravity, but remember, it could be bigger or smaller. We don't really, same size as gravity. We don't really know when it's at the top of the circle without crunching some numbers. When we go to draw the diagram, we just know the direction, not how big it is. What about the bottom of the circle, though? Which way does the normal force act to the bottom? Upwards, toward the center of the circle. The normal force will always act toward the center of the circle. Now, that normal force is going to be bigger than the force of gravity. We know that because if it wasn't, it wouldn't go in the circle. It would fall out of the circle. If gravity is bigger, then there wouldn't be a net force towards the center. Therefore, there wouldn't be a centripetal force. Therefore, it wouldn't go in a circle. All right, so next step, once we have Freebody diagrams drawn, this goes back to last unit. We did it literally 100 times or more in our last unit. What's the next step? F net equals the sum of the forces. In this case, F net is equal to Fg plus Fn. And in this case, F net is equal to Fg plus Fm. Whether you're talking about the top of the circle or the bottom of the circle. Remember yesterday we alluded to this? If we're at the side of the circle, then we still have to add the forces together, but we're not adding the forces together like this. We're adding them together as a two-dimensional vector diagram, right? So you'd end up needing to do components in the Pythagorean theorem. We won't do that, though. What's F net also equal to? Yeah, technically it's m times a, like it always was in our last unit, but a is the centripetal acceleration, which is v squared over r. So Josh, you're right. The net force is mv squared over r. In other words, the net force is the centripetal force. Remember we said earlier on in this unit, the centripetal force is always caused by something. It's never just on its own. It's always caused by something. Well, in this case, it's actually caused by two things, gravity and the normal force. Gravity, by the way, is m times g, and the normal force is just Fm. Replace Fg with m times g again. Now, if I asked you to solve for the actual weight of a person inside this cart, then you would just say mg, done. Simple. You want to find actual weight, it's gravity, m times g. If I wanted you to find the apparent weight of a person inside an elevator, or sorry, not an elevator, inside a roller coaster, what variable are you solving for? Fn, right? Just like it was with elevators. In elevators, you solve for the apparent weight, how heavy somebody felt on the floor of this elevator. Then you would solve for the normal force, the force of the floor. That's exactly what you would do here. Solve for Fn. It's not unlike, in fact, it's a lot like those elevator problems. Same two forces, just at mv squared over r instead of m times a. Okay, equations look exactly the same. The only difference is going to be the signs, positives and negatives. We don't worry about signs yet because we haven't subbed in numbers. But as soon as we sub in numbers, then we got to worry about the signs, the positives and negatives. Okay? Next step is to sub in those numbers. So let's look at the signs here. M times G, gravity will be at the top, positive or negative? Negative because it's acting down, right? What about the bottom? Negative because it's acting down. What about the normal force at the top? Negative because it's acting down. What about the normal force at the bottom? Positive because it's acting up toward the center of the circle. Now, this is the trickiest one here. mv squared over r, the net force, the centripetal force when you're at the top of the circle is? Yeah, centripetal force is the net force. It acts toward the center. If you're at the top, the center is below you, down from you. So that's going to be a negative value. Don't worry about that until you sub numbers in, but as soon as you put numbers in, then you got to worry about it. What about the centripetal force right here? Yeah. How do you know the net force, the centripetal force, is positive? You get two forces acting in opposite directions. But if you're going in a circle, the total or the net or the unbalanced force has to be toward the center, which if you're at the bottom, the center is upward from you, so it's going to be a positive value. Sub your numbers in. Solve for what you're looking for. Maybe it's solving for speed or radius, or maybe it's solving for Fn, the normal force, or maybe it says what's the force of the track, which is also Fn, or maybe it says what's the apparent weight or perceived weight, which is also Fn. Maybe it says what's the actual weight, which is just, don't do any of this if you're looking for actual weight, just multiply m times g. Got it? Here's a question for you that you're going to have to answer several times on your field trip assignment coming up in what is it, 29th? 3 weeks. Is it 3 weeks? Yeah, 3 weeks from today. Yeah. One of the questions that you're asked several times there is how many G's are experienced, the G force experienced. What do you think you'd do there? If I asked for how many G's this person experienced at the bottom of the loop, how would you find it? How heavy do you feel versus how heavy you really are? It would be the apparent weight divided by the actual weight. So you'd solve for Fn, whatever that worked out to be, and you divide it by m times g, and you get the number of G's. And if that worked out to be 2, then that would mean you'd feel twice as heavy as you really are. If it worked out to be 6, then you'd feel 6 times heavier than you really are. We watched that video, I think it was last Friday, of the fighter pilot or the astronaut, whoever it was, that was in the centrifuge, experienced G-lock. Remember, he kind of went, and then he kind of passed out and just kind of fell because the blood rushed away from his brain. Remember, that got up to like 9 or 10 G's or something like that? Right? That would be his apparent weight, how heavy he feels, divided by how heavy he actually is. We could calculate that quite easily in that situation. All right? Okay, you had 2 questions for homework last night. We're going to take a look at those 2 questions here right now, and then we're going to do another example in just a moment here. 264, questions 1 and 3. We'll do both of these, okay? Number 1 says, using the information in the example, which is this diagram right here, what's the tension of the rope at position A? So let's go to the top of the circle, position A. Gravity acts down, and normal force acts down. Oh, wait. What is this tension thing? They called it Ft. What did I call it? Fn. Does it really matter? No, you want to call it Ft, you go ahead, call it Ft. That is absolutely fine by me. Okay, as long as you know that there's 2 forces, and as long as you know what those forces are, what you call them is really irrelevant. I just call it Fn because I want to be consistent with those roller coaster problems, right, and make it look exactly the same. All right, we're going to solve for the tension in the rope or the normal force at that point. Let's say F net is equal to Fg plus Fn, same as we did in our review a second ago. F net is also equal to what? Dylan, what F net is also equal to what? Josh knows, right? Josh, F net is also equal to? Good, mv squared over r. Fg is m times g plus Fn. Still haven't subbed in signs. How come? We still haven't put in positives and negatives because we still haven't put in numbers. We don't put in signs until we put in numbers, right? Just like those elevator problems or whatever. NV squared over R, what do we got here? What was the mass? 1.5 kilograms. V is 3, right here, over R, 0.75 meters. Somebody yesterday asked me, it might have been Ben, I'm not sure, said, what's the difference between M times V squared over R and M times V squared over R? Zero difference. So it doesn't matter what you do first, doesn't make any difference, you get the same thing. 1.5 times 3 squared divided by 0.75 equals 1.5 times 9.81 plus Fn. We're not going to sub in a sign for Fn because we haven't subbed in a number for, right? But we are going to worry about the signs now for mv squared over r and m times g. Gravity is what? Negative. Yesterday I put the negative in front of the 1.5. Today I'm putting it in front of the 9.81. Does it matter where I put it? No, that term is negative. However it becomes negative doesn't really matter. What about the centripetal force? 1.5 times 3 squared over 0.75, positive or negative? It's also negative because you're at the top of the circle and the net force, the centripetal force, points towards the center. Okay, let's figure this out now. Let's say 1.5 times 3 squared divided by 0.75 gives me negative 18. 1.5 times 9.81, 14.715. It's negative. How do you take the 14 over? Add it. Yeah, so this is going to be, what, 3 point something? It's going to be negative 3.285. Which we're going to round to 2 digits. So in this situation, like I know this is a bucket of water or whatever, but let's say this is a person, okay, in this situation. Does this person feel lighter or heavier than they really are? The actual weight of this person would be gravity. In other words, 14.7 newtons, right? How heavy does the person feel? 3.3. So if you wanted to find the number of G's or the G-force, you would say the apparent weight, bless you, 3.3 divided by the actual weight of 14.7. So it would be 0.2 or something like that. 0.2, 0.25. You'd feel lighter. Now, that's not to suggest that at the top of a loop on a roller coaster, you always feel lighter. In fact, when you go to the amusement park in 3 weeks for your field trip, you will feel heavier at the top of the loop than you feel at the bottom. What's the difference? Why in that situation do you feel heavier at the top, but in this situation you feel lighter? How would you change this question to make the apparent weight or the normal force bigger than it is? Ben? Yeah, you make it go faster. The faster it goes, the harder the track has to push down to keep you in the track, to keep you in the circle, and the harder the track pushes, the bigger the normal force, the bigger the apparent weight. Does that make sense? You will, when you go around that double loop, or even the single loop on the Mindbender, on your field trip in 3 weeks, you will experience a different normal force at the top than at the bottom. At the bottom, it will be higher than it is at the top. But in both cases, the normal force will be greater than your actual gravity. So you will feel heavier all the way around. In fact, if you've never ridden one of these before, like an upside down loop, if you close your eyes, or if you look straight forward and don't look sideways to be able to perceive things upside down, you will not know whether you're right side up or upside down. You'll be simulating gravity essentially wherever you are, and you will not be able to perceive your orientation, whether you're right side up or upside down, because you'll be the track will be pushing on you stronger than gravity does at the top and the bottom. You'll feel heavy up and down, whether you're at the top and the bottom of the circle. Does that make sense? Okay, so think about that as you go around that. Okay? Go around it twice. One time, look sideways and get the sensation of everything being upside down, the earth being upside down. And then the next time, close your eyes. And you won't, like, especially when you go through that double loop and you keep going, you'll have no perception as to what's up and what's down. Okay, how many people got negative 3.3 there? We got negative, right? They said down, I said negative. Potato, potato. Oh yeah, let's take a look at question number 3 now. A 0.98 kilogram rock is attached to a 0.4 meter rope spun in a vertical circle. Tension on the rope at the top is 79 newtons down. What's the speed of the rock? Okay, let's draw this. We're at the top of the circle again. Here's the rock. Here's gravity. Here's the normal force, or how many people call that Ft? Okay, how many people call that Fn? Okay, whatever, it's the same thing, right? Potato, tomato, right? We're going to say F net, okay, equals Fg plus Fn. F net is mv squared over r. Whoops, made a mistake here. What did I do? It's not mv squared over r squared. It's mv squared over r, right? Careful with that. Okay, let's sub in some numbers here. 0.98. Do we know what v is? Nope, that's what we're looking for. R is 0.40. M, 0.98. 9.81. Okay, what's Fn? The tension, 79 newtons. Okay, let's worry about some signs here now, positives, negatives. Because at this point, listen, I just sub numbers in. I got to worry about positive, negative here now, right? What about gravity, positive, negative? Negative, right, because it's down. So put in a negative. I don't care where you put it, in front of the 0.98, in front of the 9.81, doesn't matter. What about the 79 Newton tension? It's also negative. Now, notice over here, this one's trickier. I haven't solved for V yet, but I've started subbing numbers in for mv squared over r. So I got to worry about positive and negative for that. Is it positive or is it negative? It's negative because it's acting down as well. Okay, let's see what we got here. We're going to say negative 0.98 divided by, negative 0.98 divided by 0.4 gives me negative 2.45 over here. Let's say negative 0.98 times 9.81. Okay, that gives me negative 9.6138. Now let's combine these terms over here on the right-hand side. Negative 9.6138, subtract 79. Let's take the 2.45 over by dividing. $36.16, let's square root that. Gives me 6.01. Hey, guess what? That's the answer. Listen, lots of the things you do in physics, people could say, well, when are we ever going to use that in real life? Well, lots of you may never use this in real life. Like you can clearly see that if you were to become a roller coaster designer, you would need to use this, right? Most of you are not going to become roller coaster designers. So why do we do it when most of you aren't going to ever use it? Well, because you're smarter when you've learned it. It means you become a better problem solver, whether it's a problem solver in physics or whether it's a problem solver in business administration, or you become a lawyer and you have to solve problems, whatever. You're a better problem solver when you could solve this or any other type problem. Okay. And who knows, maybe some of you actually will use this direct thing at some point. All of you will 3 weeks from now, but beyond that, who knows? Is that okay? You know from experience, from the demonstration that we just did with the keys, that if something's going in a circle, a vertical circle, but it's not going fast enough, then it won't stay in the circle. Like you can imagine if you get your toy car, that Matchbox set, you get that toy car moving really, really fast, and you get it going really, really fast, and it goes all the way around that vertical circle on the little toy car track. You know intuitively, even as a 5-year-old, if it's going too slow, then it doesn't make it all the way around. There is a minimum speed at which it can go before it begins to fall out of the circle, before it doesn't go in a circle anymore. What is that speed? Well, take a look at these keys again just for a second, okay? Right now I'm going faster than they need to go. As I slow down, this would be about the minimum speed, right? You can pretty much see them starting to fall out of the circle. You see that? They're going barely fast enough to go in a circle. How hard is this string pulling at the top when they begin to fall out of the circle? How hard does the string need to pull? Not at all. So when I'm swinging them really, really fast, okay, you can see that these keys are trying to go out in a straight line. This lanyard has to pull in quite strongly in order to keep them from going in a straight line. But as I slow it down, the lanyard doesn't have to pull in at all. That's the minimum speed. So in other words, when solving for the minimum speed, the normal force, which in this case is provided by the lanyard, which in the case of a roller coaster would be provided by the track, the normal force is 0. So what you're going to do is say F net is equal to the sum of the forces cross off Fn, because at minimum speed it's 0, and then sub in mv squared over r equals m times g. You notice a little bit of a simplification I can do here? Make this a little bit neater, tidier. That's just canceled. That's good news. That means that in 3 weeks when you're on that mind bender, it doesn't matter whether you're on the seat next to a 50-pound child or whether you're in the seat next to, let's say they're doing some kind of test where they have 200 kilograms of sand. That's how they do their tests, by the way, is they put sandbags in the seats. Doesn't matter whether it's a 50-kilogram child or a 200-kilogram bag of sand. Doesn't make any difference. If you're going to make it around the loop, you're going to make it around the loop. If you're not going to make it, you're not going to make it. The mass is irrelevant. The mass cancels. So we sub our numbers, we solve for V. Solve for V when Fn equals 0. That gives you the minimum speed that it can go and still make it around the circle. Let's take a look at example 5.6 on page 562. It says a 700-kilogram roller coaster car full of people goes around a vertical loop that has a diameter of 50 meters. What's the minimum speed that the roller coaster car have at the top of the vertical loop so it stays on the track? Hey, why are we looking at the top of the loop? If this car is going to fall out of the loop, where's it going to fall out? at the top, right? It's not going to fall out at the bottom. The track is there pushing up. If it's going to fall out, it's going to fall out at the top. So if it's going too slow, like at the bottom, it doesn't matter how slow you're going. At the top, it matters. Going too slow, you fall out at the top. So let's analyze the top. Here's the roller coaster cart at the top. Here's the force of gravity acting down. Here's the normal force. And we'll say at the top of the circle, F net is equal to Fg plus Fn. But since we're looking for minimum speed, what do we do to this equation? Get rid of Fn. The normal force is 0 when solving for minimum speed, only when solving for min speed. mv squared over r equals m times g. M cancels. We're looking for v. The r goes up by multiplying, and then we're going to find v by square rooting everything. The square root of g times r. So it's the square root of 9.81 times the radius, which is, oh, that was close. That was close. Josh, look like you're ready to give it to me. What's the radius? Right. That was close. I almost said 50. 25 meters, because the diameter is 50. The radius is 25. Square root of 9.81 times 25. Let's figure that out now. $15.66. What happens if you're going 16 meters per second? You get around the loop. Barely, but you do it. You get around it. What happens if you're going at 15? You're going to fall out of the loop. But understand, like, you're going to fall out of the loop, but you're not going to, it's not going to be like you're going around like this at 15 meters per second and then all of a sudden do this, right? When you're moving at 15 meters per second at the top here, what happens? You fall out of the loop, but since you're already moving, your path will be, what would the shape of that path be? It's a parabola. It's projectile motion at this point, right? You're not going to fall straight down unless you were stopped. Then you fall straight down. If you're moving horizontally, you'll keep moving horizontally as a projectile. So if you're lucky, you may end up catching up to the track again. I wouldn't want to count on that, though. Hey, does it make sense? Solving for minimum speed, set n, the normal force, equal to 0, and then solve for v. Take a look at these two questions, please, on page 262. Number 2, what's the maximum radius of a roller coaster loop? Go around a speed of 20 meters per second, go around safely. This is the same question, right? Except instead of saying, look, here's the radius, how slow can you go before you fall out? We're saying, here's how fast you're going, how big can you make the radius before you fall out? You're going to solve it in exactly the same way. Top of the circle, we have gravity and the normal force acting down, except that really in these cases, the normal force is equal to 0. So we cross that off. Some of you will just not even include that in the first place. We'd say mv squared over r equals m times g. We cancel out the mass, which is good because we don't know what the mass is here. V squared over r is equal to g. Now we're solving for r. Take that up by multiplying. It becomes g times r. And then we got to take the g over by, how? By dividing. If you're solving for r, take the g over by dividing. V squared over g equals r. So that's equal to what? 20 squared divided by 9.81. 400 divided by 9.81. 40.8 meters. So if you go bigger than that, then you're going to fall out of the loop. Not straight down, but off in a parabola. If you go slower, or a smaller loop than that, then you're fine at that speed. So you either need to make, if you're going too slow, you either need to speed up or make the loop smaller. Does that make sense?